Hey all, welcome to your online portion of AP Chemistry. We're going to talk through things online a little bit so that when we are in person, we can work through some of the questions together. So in these slides, you'll see light blue slides that I skip over. Those are the slides we're going to return to together in class. So let's get started. All right, when you are, as we're moving forward in AP Chemistry, we're always looking towards the test and some things that the test is going to expect you to know. You should know your base units. So when we're talking about measurement, measuring something in length, measuring something in time, measuring something's volume, measuring something's mass, what are your base units going to be? So, typically, we're going to have things like liters, grams, something for, meters. Something for time would be seconds. Your base unit for time would be seconds. Your base unit for temperature is going to be Kelvin. In chemistry, we're going to deal with Kelvin a lot. Kelvin and Celsius are really easy to go back and forth between. That's one of the things they're going to ask you to know also. So basically what you're going to do is take your temperature in Celsius and you're going to add 273. So Celsius plus 273 is going to equal your temperature in Kelvin. So it's a pretty easy flip between the two, but we are going to use Kelvin in chemistry more than we use Celsius. You should also know the prefixes. In the metric system, you're probably already familiar with them. The only ones we really deal with on a consistent basis in chemistry, we're going to deal with kilometers a little bit, but mostly the small ones like milli, micro, nano. So if you know any prefixes, know those four and how to convert between base units and prefixes. All of this is covered in Chapter 1. If you aren't comfortable with any of these things, going back into Chapter 1 and practicing them is a good idea. You can also come to office hours with me, and we can walk through some examples together until you are comfortable. Okay, so we're going to know our base units. We're going to know our prefixes. We're going to know our conversions within the metric system. We're going to know how to convert between Celsius and Kelvin. And then conversions with derived units. This is really the step up. All of this stuff we really did in chemistry. It's kind of like high school level standards. So conversions within derived units, those are going to start to be your college level standards. So by derived units, I mean something that you can calculate to, like volume. If you take length times width times height, you're going to get volume. So we don't necessarily have to measure volume. We can derive it from length, width, and height. Same thing with density. So density, we can't actually measure. We have to derive it. And so density, you're going to take your mass and you divide it by your volume, and that's what is going to equal density. So conversions with derived units is kind of the next step up on your conversion skills. Again, these practice problems are in Chapter 1. They were in your summer homework. So if you have questions on these problems from Chapter 1, don't just throw them aside. Let's work towards proficiency in this. We definitely want to take on this new attitude in AP Chem where you work and work and work until you get the answer. Just keep at it. Be persistent, be determined, and don't just let problems slip to the side. You want to have as much experience and as much comfort level as you can going into those situations where you have to apply this to a new situation or create with it in a new situation. And so let's make this our first skill that we really keep after until we understand it. Again, if you have questions on doing any of those problems in chapter 1 where you're converting with derived units, let me know. We can go through this stuff together. All right, other things you should know from chapter 1. The list goes on. You should be able to tell me what a physical property is, what a chemical property is, and what the difference between those two are. Again, we talked about this a lot in chemistry at the beginning of the year, so we're not going to talk about it here. You read through it in chapter 1. You did some practice problems with it in chapter 1. If you have questions, definitely come see me. Intensive versus extensive. Here's some new vocabulary for you. So as I lecture through this, it's really easy to listen to me as if I am a calming TV show, because my voice should definitely be all over the radio, right? Maybe not. But anyway, as you're listening through this, instead of just listening, it's helpful if you engage. So I'm about to tell you what intensive and extensive properties are. It would be a great thing for you to pause this video, try to write out a definition, commit yourself to a definition for both, and then listen and see if my definition matches up with yours. All right, so intensive versus extensive has to do with if the property changes because there's more matter present. So if you think about like a marshmallow, if we have a marshmallow versus we have like a whole bowl of marshmallows, right? If the property changes between situation A, our box of marshmallows, and situation B, our single marshmallows, then that's going to be an extensive property. Extensive is going to be dependent on the amount of matter present. And then intensive is going to be not dependent on the amount of matter present. So something like mass. Mass is going to change between our box of marshmallows and our single marshmallow, right? So mass is an extensive property. Whereas color is not going to change between our box and our single marshmallow, so color would be intensive. Volume is another one here. Boiling point would be intensive. It doesn't matter if you have a teaspoon of water or a swimming pool of water. The temperature at which it's going to boil is always going to be 100 degrees Celsius. So that temperature is what we call boiling point, the temperature at which liquid turns to gas, and it's consistent no matter how much matter is present. So that would be an intensive property. All right, significant figures. So here would be another good place before you read through this slide to pause it and say, okay, zeros. We talked a lot about zeros in general chemistry. When are they always significant? When are they never significant? And when are they sometimes significant? And that's laid out on this slide. If they're sandwiched zeros, they're always significant. If they're in the beginning of a number, they're never significant. If they're at the end, then they're always. Then they're sometimes significant. They're significant if a decimal point is present. If the decimal point is not present, they're not significant. So really what this is getting down to is the difference between significant and non-significant numbers. So when we take measurements, let's say off a beaker, if you are reading the measurement off of a beaker, it's going to be significant. But if you're not reading the number off of a beaker when you're taking your measurement, then the zero that's present is just a placeholder. And placeholders are what we call non-significant numbers. So for example, if I have the number 0.01. For example, that 1 is an integer, a non-zero integer, and non-zero integers are always going to be significant. So that 1 was read off of our beaker, but these zeros in front, they weren't actually marked on our device. But we still need them. They have to be present. Otherwise, this 1 doesn't have the same meaning, right? We want it to mean 100th of something. We don't want it to mean 1/10 of something or 1 of something. So we need these zeros as placeholders to keep the meaning of the number the same, but we didn't read them off of our device. It makes them placeholders and non-significant numbers. So things in the front can be placeholders. Things in the back can also be placeholders, like these 3 zeros. They're holding the place value of my 4. I want that 4 to mean 4,000, not 400 or 4, right? So I need these zeros to hold that place and give that 4 the value that it deserves. But I didn't actually read these numbers off of my device, and so they are non-significant numbers. If I were to put a decimal point at the end, however, or if I had other numbers that followed it, then I am indicating to you that those zeros were read off of my device. And so now they become significant. All right. Again, if you have questions on significant figures, significant versus non-significant, there's a couple things you can do. This is also in chapter 1. You can go read that section again. You can do the practice problems and try and apply this knowledge. You can come to me. We can go through this together. Also, I have a couple different interactive packets that try to walk you through this in different conceptual, applied to different concepts or conceptual situations. And so sometimes that helps you to wrap your brain around this. And I can definitely give you that if you want to kind of hash this out a little bit more. Now, here's the deal with sig figs in AP Chemistry. Significant figures, it's nice to have a ballpark and know about what you're supposed to keep, because otherwise you're going to be writing until your hand falls off, because your calculator is going to give you 15 decimals. And if you write out all 15 of those decimals all the time, you're definitely going to give yourself arthritis, and nobody wants that. So it's nice to know how many sig figs to keep and have kind of a ballpark of where your number stays accurate, but what you can actually cut off and not actually write out. However, this whole concept is only worth 1 point on the AP exam. So again, this is why we're not going to spend a whole lot of time with this together, because it's nice to know. It definitely affects your work if you are in a live lab, but it's not going to affect your life a whole lot on the AP Chemistry exam. It's 1 point. There is one question in one of the free responses on the AP exam where they test you to see if you can write your answer in sig figs, correct sig figs. And if you can, then you get the point. And if you can't, then you lose that 1 point, and then life goes on. So it's really not worth a whole lot of points in your AP Chem exam life. So my recommendation would be feel comfortable with this, comfortable enough to move on, but don't spend your whole weekend trying to figure out sig figs. Okay, last thing on here that you should be able to do, you should be able to write numbers in scientific or exponential notation. You should be able to put them in, take them out, read them off a calculator, stuff like that. Again, not a skill we're going to spend time on in AP Chem, but if you are not comfortable with this, let's talk and go through a couple examples until you are comfortable with this. Oh, that is definitely not what I meant to do. Give me a second. All right, here's one of those light blue slides. We'll go over this together in class. And we're on to chapter 2. Welcome to chapter 2. All right, more things you should know. And if you are not comfortable with these things, then let's you and I talk until you are comfortable with these things. Things like protons, neutrons, and electrons. So these are the 3 subatomic particles. They make up every single element. And they are charged. You can see in this column, I do list out actual charges, but what you need to know, you definitely do not need to memorize this number. What you do need to know are relative charges for all of these. So if a proton is a +1, then an electron is a -1. Same thing with mass. You can see I have listed out actual mass for anyone who's interested in that. Again, you don't need to know actual mass. You need to know relative mass. So if a proton is a 1, then a neutron is a 1, and then an electron is a 0. And here's one of the things where we are going to call back onto those significant figure ideas. The electron's mass is not actually 0. An electron is not massless. Electrons are made out of matter, and all matter is going to have mass and take up space, right? The reason we say an electron's mass is relatively 0 is because if you were to add up all of these, just 1 proton and 1 electron, or let's say 1 proton, 1 neutron, and 1 electron, then the electron's mass, 0.01, 2, 3, 5, 4, 8, 6, written like this, if you take it out of scientific notation, is not actually going to have an effect on the mass of a proton or a neutron until you get way out here into the 10,000ths position. So if you're rounding off to the 1 tenths, hundredths, or thousandths decimal, then this mass of an electron is not even going to have an effect. It's just going to get rounded off, and that's what we call statistically insignificant. If it gets rounded off because of sig figures, we can assume that it's 1 and move forward with that assumption without actually affecting our answer. And then as we get more protons and neutrons, this becomes even more true. Okay, other things you should be aware of. First of all, we're going to use AMUs a lot more than we're going to use grams. So an AMU is an atomic mass unit. It does have an actual mass, and you can see that actual mass boxed in purple, but it operates more like a relative mass. So we can say a proton has a mass of 1 AMU, and a neutron has a mass of 1 AMU. Therefore, a carbon atom has a mass of 12 AMU. And it's a lot cleaner to deal in AMUs or atomic mass units than it is to deal in grams. I mean, if we have to add up this 12 times on our calculator and then round off to correct sig figs, it just gets a lot messier and a lot bulkier. So that's why we use AMUs. Other things you should know the conversion between angstroms and meters. Now, an angstrom is an interesting unit in the metric system because we don't refer to it very often unless you're a chemist. And if you're a chemist, a diameter of an atom is about on the order of an angstrom or a couple angstroms. And so it becomes a really easy measurement for us to use. And again, kind of like the AMU gram thing, it just is so much cleaner to measure things in like 4 angstroms rather than like 4 times 10 to the negative 10th meters. And so it is a distance. And you don't actually write it A. The unit actually is A with a little circle on top. So the unit for angstrom is this. But 1 angstrom is 10 to the negative 10th meters. So that's a measurement that you should memorize and have in your back pocket because it's going to be thrown around, especially when we get into things like atomic structure. All right, subatomic particles applied. So this would be a good place to pause the recording and try and answer these questions. If you change the atomic number of an element, let's say carbon 12, for example. What if you change the atomic number? What if you change the mass number? And what if you change the charge? So if you change the atomic number, which is essentially changing protons, right? You're going to get a different element. If you change the mass number, you're going to get an isotope, which is the same element with a different mass. And if you change the charge, which is changing electrons, mass number would be changing neutrons, the charge, you're going to get an ion, which is the same element, but it's charged positively or negatively. When we write isotopes, let's visit this a little bit. You may see them in your book a couple different ways. You could see, let's see, what am I asking for? An isotope with carbon's isotope with 6 neutrons. So that's carbon-12. Okay, so you could see carbon-12. You could see the actual word carbon spelled out, -12. You could see carbon with a 12 up here, or you could see carbon with a 12 up here and a 6 down here. Now, here's the deal. Notice in all 4 of these, the thing that's always present is the mass number, because the symbol carbon means that you have 6 protons. If you have 6 protons, you have carbon. If you have carbon, you have 6 protons. That's a non-negotiable, and so you don't necessarily need to state it twice. Here at the bottom one, down here in the bottom right corner, notice we do state it twice. You can actually list both. That's very kind of you. You are saving your reader from going to look at a periodic table if they are not already familiar with carbon. So sweet. But you don't actually have to, because most people in the chemistry profession, especially if you're dealing with something so common as carbon, are going to know that carbon has 6 protons, and you don't actually have to list it twice. But what you do have to list is the mass number, because not all isotopes have the same number of neutrons, and so you need to specify which isotope you're talking about. Does your carbon have 6 neutrons, like carbon-12? Does your carbon have 8 neutrons, like carbon-14? It makes a really big difference on how that carbon is going to behave. And so you need to specify which one you have. So in all of these cases, you're always going to list the mass number. All right. Go ahead and try this. Each of these problems, you're going to do 23 or 22, not 23. But each of these problems comes from an actual AP test, and the College Board today gives you 1.5 minutes per question on the test. Now, some of these questions are going to take you 10 seconds, which is great because it gives you more time for questions that are going to involve things like calculations or looking stuff up on a reference sheet or finding something on a periodic table of an element. So the fast ones you definitely want to answer fast if you can. But if you can't, here's what we shoot for. Our goal is about 1.5 minutes per question. You will spend longer than that on some of the questions, especially some of the calculation questions. So take a minute and answer this question, and I will time you for 1.5 minutes. Go. Okay, I lied. I'm not actually going to give you 1.5 minutes. That was 30 seconds. And I think you should be able to answer this question in 30 seconds because you should recognize that 26 would be the protons, which automatically gets rid of these. And then 56 minus 26 is 30, so that should be your neutrons. And you don't even need to figure out electrons because you already know it's A. But in something that's neutral, remember, if it's not neutral, it's going to have a charge up here in the upper right-hand corner. And since it doesn't have a charge, protons and electrons should be the same. So you should have come to the conclusion of A. If you have questions on that, make sure you write them down and we can deal with those in class. Okay, let's keep going. Isotopes. So again, this is a concept that we talked about a little bit in chemistry, but I just want to revisit weighted average real fast. So if you are adding up two things, let's say you're adding up 14 and 15, and you want the average of those, you're going to add them up and divide by 2. So when you do that, what you're actually doing, follow me here, 14 divided by 2 plus 15 divided by 2. We can kind of parcel it out a little bit here, or you can parcel it out even more and go 1/2 times 14 plus 1/2 times 15. So you can see what we're doing here is we're actually finding an average where each of these 0.5 times 14, also known as 50%, plus 0.5 times 15, again, also known as 50%. Okay, so what you can see that we're doing here is we're taking two numbers, taking 50% of them and then adding them back together, and that's what you get an average. If you're averaging three things like 14, 15, and 16, you're going to divide by 3. So what you would actually be doing is multiplying each of, well, let's do this. Oh, no, that's not correct. You're going to be multiplying each of these by 1/3 or 0.33 times 14, 0.33 times 15, 0.33 times 16. Okay, so no matter what you do as an average, when you do a straight like arithmetic average, you're giving each of the numbers in your sample an equal amount of say in the answer. And what we would say is that's an equal weight. They all get an equal weight. They all impact the answer the same. Well, when you are dealing with isotopes, here's the deal. Your isotopes aren't going to exist in nature in the same amount. So if we're dealing with chlorine, for example, here's two very common isotopes, chlorine 35 and chlorine 37. So chlorine 35 shows up in nature 75.78% of the time. We call that a percent abundance. It is 78% of the abundance of chlorine that you would find in nature, whereas chlorine 37 is only 24% abundant. And so we don't want to do an average with these two where they both apply equally to our average weight. We want to weight them unequally. We're going to weight them according to their percent abundance. So it's the exact same formula. You're still going to take, your sample and multiply it by the abundance. So in this case, we would do the mass of chlorine 35 and multiply it by the percent abundance for chlorine 35. And then we're going to add that to the mass of chlorine 37. And we are going to multiply that by the percent abundance of chlorine 37. So it would look like they tell us a mass here, 34.969 AMU. And we're going to multiply that by 0.7578. Remember that when you are multiplying, you want to take this out of a percent form and put it into a decimal form. And then chlorine 37 has an atomic mass of 36.966 AMU, and we're going to multiply that by 0.2422. Okay, go get your calculator, see if you get the same answer I get. 34.969 times 0.7578 plus 36,966.2422. Okay, so what you should get is an average. It should be between your two numbers. It should be in between your two masses. And this is a self-check you should do. If the number you get is not in between 34.9 and 36.9, then you did something wrong. The number you should get is 35 point, and we're keeping 4 sig figs, 45 AMU. If you didn't get that answer, what I would suggest that you go back and look at what you typed into the calculator and look at your parentheses. It's really, really important that you bracket this before you add it. You have to force your calculator to do the correct order of operations. And if you don't put it all in parentheses, it will add before it multiplies and it'll throw you off. Okay, so that is a weighted average. Now, here's the deal. The College Board assumes that this is a chemistry level standard and not an AP chemistry level standard. So it's pretty unlikely you're going to be tested on how to calculate a weighted average, although what I have learned over the years is don't put anything past the College Board because they are wild creatures. However, I think it's important that you understand how atomic mass is calculated. So for example, if you look at the periodic table and you look at carbon-12, you're not going to see an atomic mass of 12. You're going to see 12.011. And what this tells me is there's a couple different isotopes. There's an isotope of carbon-12, and then there's some isotope that is bigger than 12 because the average is bigger than 12. So it could be carbon-13, or it could be carbon-14, or it could be both. And so I know all of this just by looking at the atomic mass on the periodic table. The periodic table is this awesome tool for you. You just have to know how to use it. And this is one of those ways that you can know how to use it. The other thing that I can know from this is that the vast majority of my abundance is going to be carbon-12. Probably somewhere around 99% of the abundance of this element is going to be carbon-12. And then there's going to be a really small portion of one of these two, or maybe both. Whereas if you look at something different like chlorine, for example, chlorine's average 35.45. So it's pretty in the middle of your values. So if you didn't know anything about the isotopes of chlorine, there's definitely one that's smaller and there's definitely one that's bigger. But they both have significant abundances because it's not real weighted towards one or the other. The other thing, well, I guess on this, you could maybe stake a claim that the mass that your average is closer to, 35 versus 37, you could make a statement, take a stand and make a statement that the abundance, there is more chlorine-35 in the environment than there is chlorine-37 because the calculated average atomic mass is closer to one than the other. Okay, last fun fact for you to know about this. So you could be able to tell me what isotopes are present. You could tell me what isotope is present in more abundance. And then the other thing that you might be able to tell me, that you will definitely be able to tell me, is there is no atom that weighs 35.45. We calculated this, right? This is going to be on the periodic table, but there's no chlorine atom that actually weighs 35.45 AMUs. It's a calculated number. It's not an actual mass. So that's kind of the third detail that you should definitely know about weighted averages. Fun fact, this is exactly how your grades are calculated in most classes. So if you are ever trying to calculate your grade, you should definitely be using your points times your weight of those points in the gradebook. Like, for example, in a traditional AP Chemistry course in the past, I've had tests be worth about 70% of the grade. And so you would take all your test points here and you'd multiply them by 0.7 because that's the weight of those points. So now you can calculate all your grades all day long. Isn't that super fun? All right, we're going to do a weighted average practice together in class. Let's talk through types of structural representations. So through your book, you're going to see a bunch of different ways represented. Now would be a good time to pause this and think to yourself, what would be the point of using these different representations that are all representing the same molecule? These are all representing methane. So this would be a good time to pause. And hopefully what you think of is this method, this first method here, this is going to show connection. So if what you care about is how all the atoms are connected together, this is by far the simplest way to represent methane. And you would go with this representation. This other one up here on top shows the geometry. So the angles between the atoms are shown pretty accurately here. And so you may want to represent the geometry of the molecule. And so you would use something like this. Notice that they use this triangle here to try to represent that this hydrogen is coming towards you in the plane. And then they use a dashed line here to try to represent that this hydrogen is going back away from you, like into the plane or into the paper. Okay, this one is called a ball and stick model. And this is basically a better version of the geometry influenced model. If you have a computer and your computer can generate an image, then a ball and stick would be a better image to use. If you're using pencil and paper, like a lot of us are, then this one up top would be just fine. Okay, last image down here on the bottom. This one's called a space filling model. And so you may see this type of representation if it's really important to know how much space the actual molecule is going to take up, because that sometimes forces other molecules into different shapes or forces certain attachments. You can think about a lot of the drugs that they design to target certain like viruses or target certain bacteria. They'll make a molecule that will fit into a very specific place on the surface of the virus. Well, if you are trying to do that, then how much space your molecule takes up becomes really, really important. And so you would probably use some type of modeling program to show you those space filling things. Okay. Nomenclature. So names. Remember when we did this in chemistry and remember how much fun this was? Yes. So we need to talk through names again. And again, I'm not going to teach you this, but I do want to talk through all these systems so that you remember how to name molecules. And when you read the name, you can remember how to write the molecules. I am going to teach you one system, and that's the organic naming system, but we'll get there. Before we get there, let's talk through binary molecular compounds, ionic compounds, and diatomics. So again, this would be a good place to pause and see if you can write out how to name molecules, how to name ionic compounds, and then what do you do with the diatomics. Also, before you go, fun fact, binary just means two, which means I'm only going to give you, and the AP is only going to give you molecules that contain two elements like H2O or CO2. That would be a binary molecular compound. We're not going to make you name molecules with more things like, I don't know, Oh, well, that's actually an ionic compound. If you see something like CaCO3, for example, you would know automatically that's not a molecule. It's not a molecular compound. It's either an ionic compound, or it could be an acid, a base, or an organic compound. So we'll talk about how to tell the differences between all of these. Okay, pause, remind yourself, then we'll go through it. All right, binary molecular compounds. Remember, it's really important to tell me, you're going to tell me the prefix, which is how many of the atom, and then you're just going to name the element. So there's 1 carbon and 2 oxygen. So my name is going to represent that. So it would be monocarbon dioxide. You're always going to put an "ide" at the end of these molecular compound names. And then there's a couple tricks. So one of the tricks is if you have a double vowel, sometimes one of the vowel gets dropped. Also, if you have mono at the beginning of the word, it gets dropped. And I think they do that because there's so many compounds where the very first element listed is a mono, and so scientists got lazy and just started dropping the mono. Other than that, the system's really straightforward for binary molecular compounds. Ionic compounds, it's possibly more straightforward because for ionic compounds, you're just going to name the first ion, then you're going to name the second ion. So if you have, for example, like Na3P, okay, so you name the first ion sodium, you name the second ion phosphide, and you're done. The only catch is you have to remember how to name ions. So positive ions or cations, they are going to be named the same as the element, whereas negative ions or anions, they are either going to end in "ide" or they're going to be polyatomic, which means they end in "ate" or "ite." Okay, so next time we will start by talking through the ion names, "ate" and "ite", and we will remind each other of how to deal with that. Last thing before we go, diatomics. So remember, there are 7 elementals. There are 7 elements that in their elemental form, they exist as diatomic, so 2 atoms. Those 7 are going to be nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Notice that they make a 7 on the periodic table, and then you also have to include hydrogen, which is not in the cool 7 club. Okay, so those 7 elements exist as diatomics. So if I ask you for elemental chlorine, I'm talking about Cl2. If I ask you for elemental phosphorus, I am either talking about the monatomic form, or some of these elements have other forms. If I'm asking you for elemental nitrogen, I mean N2. If I'm asking you for elemental carbon, I just mean C, the monatomic form. Okay, solid work today. We'll talk about ions next time. Bye.